All right, turns out vegetable oil has a specific heat capacity of 1,670. So that'll do us. And we will need to work out the error. So how far off were we? Identify the liquid including the error. So for the percentage, until I get this in focus, here we go. Excuse me. Percentage error is it's absolute, so it doesn't matter whether it's positive or negative, and it's just accepted minus observed or experimental over the accepted times 100 percentiles. Righto, so we would have 1670 minus 1500 over 1670. So what does that give us? %. That's not too bad. So you'd identify it as vegetable oil with a 10% percentage error. Evaluate the precision of the data collected. Righto, so we're going to have a look at our graph back over here. And, it's not too bad. There's no overlapping of these error bars. If the error bars are overlapping with the error bars on the adjacent points, then that means that these readings are within the range of those readings. So these 2 points are not really different, but these error bars are quite small. We've got a pretty good R squared value. So those are 2 things that you would talk about. Extrapolate the graph to find the temperature at 5.5 minutes. Now, this graph would need to be extended up. If you're extrapolating it, you're going to get a ruler, line it up, and draw it with a ruler, not freehand, and work out what temperature you think it's going to be. Or the other thing you can do is put the value into the equation. So you could put 5.5 into the equation. So 20.907 times 20.9, oops, that's a 7. 20.907 times 5.5 plus 26.3, and we should get, we get 141. So does that look reasonable? Looks like it would be on the next band there. Yeah, so you can do it that way too. Identify the mathematical relationship between the temperature and the heating time, including the uncertainty of the gradient. Right. I'm going to get a fresh page for that because I don't know that I have to actually. It'll fit down the bottom of this page. Righto. Mathematical relationship from this one over here. So we're interested in the 3 equations there. So the first job, what number is this? 7. First job we have to do is get the uncertainty in the gradient. So that's plus or minus max minus min divided by 2, and we're doing the gradient, so I'll just put a little g on there. It's a bit wild tonight. Okay, so the maximum gradient, if I look at these equations, this is the maximum trend line. The maximum gradient is here, 22.1. The minimum gradient is here, 19.74. Divided by 2. So we've got 22.1 minus 19.74. Don't forget to total it and then divide by 2. 1.18. Plus or minus. Got to have the plus or minus 1.18. Rightio. Then we want the uncertainty in the y-intercept. Plus or minus, and again it's going to be max minus min, and it's in the y. Divided by 2. Go back to your equations. Here's the maximum y, 23.55 minus 27.65. It's absolute value, so it doesn't matter that the max is smaller than the min, and divide by 2. So we've got 23.55 minus 27.65 is negative 4.1. We are not worried about the negative because we've got that covered with the plus or minus out the front there. Got to divide that by 2 though. So 2.05. Okay, now we're going to go back to our equations and get the equation for the linear trend line. So it's y equals 20.907. It's this one up here, the first one, that has the r squared value with it, plus 26.3. So that's the equation. We're going to put these into it. I should have left room and done it in one go. So y equals 20.907 plus or minus the uncertainty in the gradient, 1.18, so that figure goes down there, plus 26.3 plus or minus this one here, the uncertainty in the y. Right, then we go back. We go back and have a look at what y and x represented in the graph. Y was temperature, so that's going to be T equals 20.907 plus or minus 1.18. And x on the graph was time, so we'll give that a small t, plus 26.3 plus or minus 2.05. Right, so that is the mathematical relationship. That's worth 1 mark, that's worth 1 mark, and that's worth 1 mark. So it'll be worth 3 marks.